It's a resistor in series with a capacitor and an AC source. So what do we see from Kirchhoff's rules? Well, if you take one loop around here, there's a voltage due to the AC source. That's changing with time. That's a sine wave kind of voltage. In the direction of the current, you'll find the voltage drop through the resistor. And then the charge controls the voltage change across the capacitor. So what I want to do is show you something. I don't really care about the current right now. I care about the voltage across the capacitor. This is what we're measuring with this thing. With this voltmeter, we're measuring the voltage across the capacitor. Voltage across the capacitor, it says here, it's an example of a low-pass filter. Why would that be? Here's C, here's R. You know what an RC circuit does. It takes a while to fully charge a capacitor when you put a voltage across it. It takes time because R keeps the current from being very big. And so the bigger R is, the smaller the current ends up being for any particular voltage. And the bigger the capacitance, the longer it takes to charge it up for any particular current. So R can make the current small, and capacitor can make it take a long time no matter what the current is. Both R and C control that time constant. So what happens if I oscillate my AC source faster? You saw that I could change the frequency. So let me change the frequency. The frequency goes up a lot. All right, it didn't go up that much, but yeah, went up 4 times. You can see what happens. This switches back and forth faster and faster. And you can see on the plates of the capacitor what's going on. Capacitor does not have time, given the R and the C in this circuit, and the AC voltage is switching so fast that the capacitor doesn't have time to charge up. If it doesn't have time to charge up before the AC source reverses the voltage, then the voltage across the capacitor never gets very big. Now, when you go around this loop, it has to be, the voltage change has to be 0 around a loop. So if the voltage across the capacitor never gets very big, even though the voltage across the AC source is still 10 volts, if the voltage across the capacitor is never getting very big, then the voltage across the resistor must be always big. So it must be oscillating with at about the same magnitude as the AC source. So what's going on here? This says V capacitor is an example of a low-pass filter. What does a low-pass filter mean? Well, the AC source is something like your wall. So you plug this into your wall socket, these 2 wires, instead of into this AC source. That's the same thing. And into that wall socket, you hooked up a resistor and a capacitor, and then you looked at the voltage across the capacitor. Hook 2 wires up the capacitor, look at the voltage across the capacitor. That capacitor is a filter in this sense. The AC voltage is still 10 volts. It's still swapping 10 volts back and forth. Because this thing doesn't have time to charge up, the voltage between these 2 points is going up and down, but it's not very big. I can blow up the scale here and figure out how big it is. It's something like 1 volt at this frequency. Something like 1 volt back and forth. If I went up to a higher frequency, it would be even smaller. So high frequencies don't show up here. If I plug this into my computer, if there are high frequency voltage oscillations here in the AC source or in the wall, then those will not show up at my computer. What about low frequency AC oscillations. Well, if I change the frequency, make it really small. I don't want to make it too small because it'll take forever to oscillate back and forth. But if the frequency is low, you can see that this capacitor has plenty of time, and this RC circuit, this capacitor has plenty of time to charge up. Notice that just check the voltage across the AC part. It's still plus or minus 10, much smaller frequency, of course. Now I've plugged my computer across the capacitor instead of plugging it straight into the wall. And what do I get? Well, at these low frequencies, I get close to plus and minus 10 volts. So it's a low-pass filter, meaning it lets pass low-frequency oscillations. Voltage across the resistor. Well, if this has a high voltage, you can probably guess that the voltage difference across the resistor is not going to be so high. Looks like it's about plus and minus 5 or 6. Let's make it smaller. Okay, it's going to take a really long time to oscillate, but you will be able to see at really low frequencies like this that the voltage across the resistor never changes very much. And you can see why. I mean, the voltage of the source is changing so slowly. We are charging this capacitor so slowly that the current is very, very tiny all the time. If the current is always very, very tiny, then there will never be a big voltage across this resistor. If I hooked up a wire here and a wire there, oh, don't do that, then the voltage across these two would be the same as the voltage across the resistor, and that would not be changing very much. So at low frequencies, you don't see a voltage here. But of course, across this resistor, at high frequencies, we expect to see it again. High frequencies, you see the oscillation of the voltage across the resistor right here. So at high frequencies, the voltage across the capacitor never gets very big, but the voltage across the resistor does. And so the voltage across the resistor is a high-pass filter. It lets high frequencies through. At voltage across the capacitor never gets very big at high frequencies. So when you're looking at the voltage across the capacitor, you have built a low-pass filter